converter, any chips. Yes, you got to check the diode specifications and find one that fits. Yes.
One more question is there from Aditi. Can you explain once the in-band dispersion part?
Oh, okay. Um,
Sir, you are not audible actually.
okay, so the receive antenna, I will repeat that. So in these satellite communication systems in the Ku band, the receiving bandwidth is 10.7 gigahertz to 12.7 gigahertz. That's a 2 gigahertz bandwidth. That's a massive bandwidth. So
Sir,
your receive antenna should,
excuse me,
yeah.
sir. Have you shared your presentation somewhere?
No, I'm just talking.
Okay. Okay.
I don't have slides for that. So that is 2 gigahertz bandwidth, right? So any SATCOM receive antenna for OneWeb network, OneWeb Eutelsat, or Starlink should be able to receive signals over this 2 gigahertz bandwidth, 10.7 to 12.7, but not at the same time, because you only receive one channel normally, and the channel bandwidth is only 250 megahertz maximum. A lot of these systems. So at one instant in time, you are receiving data over 250 megahertz bandwidth, and that is called instantaneous bandwidth or in-band. That is the channel. So your antenna should have a pattern that is pointing towards the satellite very precisely within this entire bandwidth of 250 megahertz. Usual beam width of these antennas is about 2 to 3 degrees. And that is a very narrow beam width, right? If you point in the wrong direction, you lose the signal, or you end up with less signal and more noise, and you lose the signal to noise ratio, and you lose data rate. So this is called, now what suppose you have an antenna like a leaky wave antenna, and when you check your pattern, normally leaky wave antennas are not used for this application, but just to make the point, if you check your pattern of your antenna over 250 megahertz, and if it changes to different directions within 250 megahertz, you are in trouble. And that is called in-band dispersion. Because the band, it's actually more than, it's not really, it's yet more precise name is in-channel dispersion. Channel bandwidth is 250 megahertz. The beam direction changes within the channel bandwidth. So that is in-channel dispersion. If your antenna beam direction changes over the whole 2.5 or 2 gigahertz, that's okay, but it should not change substantially within the channel bandwidth. So when you design antennas, you need to look into not only the total bandwidth, you need good matching, etc. over the total bandwidth, but you need good
Sir, your voice is not coming.
Yeah, you need some telecom focused antenna papers or articles in Antennas and Propagation magazine, communications magazine would probably cover this type of topics. Now I'm trying to find the best place to start. The resonant cavity antenna. So, okay, I think I can start from here. So this is how I describe the resonant cavity antennas in some of my distinguished lectures. They have many names, many advantages, from Trentini to beam steering of modern Fabry-Perot resonant cavity antennas. So we looked at introduction, and one is what inspired us already. So you can skip that part. Oh no, we didn't do the introduction. Okay, we have to do this. I don't know why Google is actually disconnecting my voice. So okay, that I know. Maybe I'm touching the space bar accidentally. Maybe that is the reason. I'll put this keyboard away. And let's see how it goes. Yes, I don't know any other antenna that has so many names. Resonant cavity antennas are also known as electromagnetic bandgap resonator antennas or EBG resonator antennas, Fabry-Perot resonator antennas or Fabry-Perot cavity resonator antennas, partial reflector surface PRS antennas, and also 2D leaky wave antennas. I think at the end of this lecture, few lectures, you will understand why they are called EBG resonator, at least some of them, Fabry-Perot, PRS. I'm not going to go to the 2D leaky wave analysis of resonant cavity antennas, but just worth saying that some experts in leaky wave antennas, like David Jackson, Esselle, David Jackson in USA, Filippo Capolino, previously in Italy, now he's also in USA. They have analyzed this kind of antennas using leaky wave theory. In the 2D leaky wave theory, not the 1D leaky waves we looked at in my lectures, but two-dimensional leaky wave antennas. And there's similarity. There's a way to describe their behavior using leaky wave theory. So that's why that name. Now, what are the advantages? Most of them are planar. Very few of them are quasi-planar. That means you have flat configuration. They are very simple configuration, and this is the configuration. So it has a resonant cavity. That's the name resonant cavity or cavity resonator, resonant cavity antennas. It has a resonant cavity.
Excuse me, sir. Your
Sorry?
slide is not moving.
Oh, okay. Yeah. I had to redo this. Because I'm looking at my slides, not the. Okay. So I'll go back to this first slide. There's nothing. Right. There's a title. Many names, many advantages, from Trentini to beam steering of modern Fabry-Perot resonant cavity antennas. It's working now, right? I can see on the Google as well. That's the outline you saw before, and we are here. So this is the configuration. We have a resonant cavity, which can be filled with material, dielectric, for example, but in most cases the resonant cavity is filled with air because air is cheap, right? And reasonably good electromagnetically, no loss. Then on top of that, the resonant is this most interesting part of the antenna, which is a partially reflecting superstructure. And the other side of the cavity, the bottom, there's a ground plane. It doesn't have to be a ground plane, but it has to be a fully reflecting surface. Fully reflecting surface. So a very easy example, fully reflecting surface is a metal plate, right? Conducting plate, and that is a ground plane. So that is fine. But you can use other types of fully reflecting surfaces, like artificial magnetic conductor we discussed previously, because that is also fully reflecting. Okay, so those are the two parts, and then we have to excite the cavity.
Again, you are not audible, sir. Excuse me, sir. You are muted.
Yeah, it was not muted actually. It was a bigger problem.
Okay, nice.
My mic was disconnected. I got it back now. Computer said could not detect the mic. Okay, let's get back to that. So you have to excite the cavity, right? So you have to feed the electromagnetic energy into the cavity. So we need feed antenna. You need at least one feed antenna, maybe several feed antennas in very special cases. So that's the basic configuration for all these antennas. All of them have the same configuration. That's basically the same antenna. Advantage is more, you can get high gain without a large feed network. If you are familiar with antenna arrays, there is another way to get higher gain, higher directivity from low gain, low directivity elements, antennas, by making an array of them. But you need the substantial feed network to combine all the feeds into one, especially if you need very high gain. Or even for medium gain, you need the feed distribution network, and the network has losses, RF losses, especially at higher frequencies, upper microwave frequencies and millimeter wave frequencies. The feed distribution network is quite lossy, so your antenna array would have poor radio frequency efficiency. But it doesn't happen here, so normally these type of antennas have high overall efficiency, not always high aperture efficiency, but I will show you some of them that has very high aperture efficiency. Yeah, I will come back to overall efficiency later. Polarization flexibility. You can design antennas, resonant cavity antennas have linear polarization, circular polarization, dual linear polarization, dual circular polarization, and so on, almost any polarization. And in fact, changing between different polarizations is also very easy. For example, if you design linearly polarized resonance cavity antenna in a particular way, and you want to convert it to a circularly polarized resonant cavity antenna, all you have to do is change the feed. For the linearly polarized antenna, you use a linearly polarized feed. If you want to make it dual linear, replace this by a dual linearly polarized feed. If you want right-hand circular polarized, replace this with a right-hand circular polarized feed or dual circular polarized feed, such without changing any other part of the antenna, especially the partially reflecting superstructure. The biggest advantage of these antennas is they have extremely large directivity band product per unit area relative to the area, the electrical area of the antenna. Their directivity bandwidth product is very large. So hence they became quite popular, and I will show you the history of these antennas. But they are not all. I mean, there are some limitations. The one limitation, probably the most significant limitations, is they are not very tall, but not very thin. Especially they are thicker than some microstrip patch arrays and slot arrays, because you need the height for the resonant cavity. Okay, this is the history. I think I believe this is the first paper on this topic, published in in transactions on antennas and propagation, but this was even before IEEE, even before IEEE. Those days it was IRE, International Radio Engineers, I think, or something. This, but the transactions on antennas and propagation exist under the organization of IRE, not IEEE. So Trentini published this paper, the subject of partially reflecting sheet arrays, and these are a couple of figures from that. He described this as a reflex cavity antenna. You know, this is like World War II, after World War II, is a waveguide era. So he used a waveguide and create something like a horn opening this cavity at the end of the waveguide and put a sheet, partially reflecting sheet or a mesh at the end of the cavity. And these are some of the other sheet configurations he used. Metal sheet to make it partially reflecting, partially transmitting. And he got this reflex cavity antenna. That's the first resonant cavity antenna, as far as I can find. Okay. So what is happening? What happened afterwards? People came up with quite different type of superstructures. The three examples are shown here. Ways of making these superstructures. One method is using a dielectric stack, right? Stack of dielectric slabs. No metal in the superstructure, they're all dielectric. Could be really cheap dielectric like FR4. So they're very cheap to manufacture. Can be done even in undergraduate projects. If you want to demonstrate or understand how an antenna works, or how to get more directivity and gain from a simple structure like this. So these are called, these are one-dimensional stack, and these antennas are inspired by 1D electromagnetic band gap structures. And I will explain how these are related to 1D EBG structures. Then the second type, in the second type, the superstructure is a two-dimensional periodic surface, like a frequency selective surface that we discussed yesterday. So it could be a slab, dielectric slab with printed metal patterns on one side or on both sides, and that's quite easy to fabricate using printed circuit board technology as a PCB, and that's a 2D periodic, or sometimes a periodic PCB. Now the third type is based on 3D electromagnetic band gap structures, like the wood pile you saw yesterday. So if you take one part of this wood pile, just one piece of this wood pile, and you can use it as a superstructure, because one section is partially reflecting and partially transmitting. If we put too many sections, it becomes almost fully reflecting, like we saw yesterday. It's almost like metal. But if you take only few, like 4 layers, that's one section, it's a partially reflecting surface. So that will meet the requirements for the superstructure on a resonant cavity antenna. So those are the things we are going to look at. Different type of resonant cavity antennas. We made a very large number of these different types of shapes. All these photos are our prototypes. This is the 1D slab type made out of FR4, very, very low cost. This is a more advanced design. And the superstructure here is a combination of several dielectric layers, 3 or 4 dielectric layers, including the air layer. This is the air layer, this is dielectric, this is different dielectric with different dielectric constants. So this part is the superstructure, and this is the resonant cavity, and this is the ground plane. So the feed antenna here is a slot. Probably hard to see. I should have other figures later. And the slot is fed by a waveguide underneath. This is another one of the latest, one of the last resonant cavity antennas we made. That's a superstructure that has different dielectric material, but you can see it's different to this. That's a superstructure. This is the cavity, airfield cavity. This is the ground plane. This is the feed element, that is a slot fed by a waveguide. This is a 2D FSS type PCB. It just looks totally dark. That is because the printed circuit, printed pattern, two-dimensional pattern is on the other side, printed metal pattern. So that's the example for the 2D FSS type resonant cavity antenna. So you said you heard about Trentini paper, but after a long time, antenna engineers did not bother about this type of antennas because they were not very exciting. The bandwidth was narrow, but it was when Alex Fersidis, this is in Ladbroke University in UK, with Yanis Vardasoglu, his supervisor, published this paper on a similar antenna with the 10% half power directivity bandwidth, HPDP 10%. That was a world record for the bandwidth of this kind of antennas. That was in 2006. And then see what happens. There's an explosion in research in this area in the next 10 years. By the time 2016 and 17, we had prototypes. That's Rahil Hashmi, one of my PhD students. We had antennas with measured half power directivity bandwidth of 53%. Another PhD student extended to 57%. With about the same gain. So you can see the gain of this antenna is 20.2 dBi. 20.2 dBi. The original Fersidis antenna is also about 20 dBi, but bandwidth improved from 10% to 57% measured bandwidth. So that is the type you saw before. And in between, there's a lot of other papers. Some of these are from my group, and others are from other groups. These are my papers. This one, this. and the others are from this as well, and the others are from other groups. You can see different configurations. They are all resonant cavity antennas. Some have non-uniform patches, so there's a kind of a periodic pattern, multi-layer PCBs, single layer PCBs, multi-layer dielectric slabs, and so on. 3-layer PCBs. They all have good directivity. All of them got directivity greater than so what is the greater? Forget the greater than 15 dBi. All of them got directivity greater than 15 dBi except this one. And people are still working in this area, so it's still a research area, but a lot happened in that period, so that's why I'm focusing on what happened and how new ideas came into the research area to advance knowledge in this area. So this is the 3D wood pile version of our, of the resonant cavity antenna. So we took one section that is 4 layers of the wood pile to create a resonant cavity antenna. The resonant cavity is here, and there's a ground plane which is little larger than the wood pile, and the feed is this. There are 2 slots in the ground plane, and they are connected to a waveguide. So looking at the field distribution animation, you can see the wave coming through the waveguide. This is the same field. The top one is the linear scale. The bottom one is in log scale. It's at the same data. Looking at the linear one, you can see the electromagnetic wave, the microwave coming through the waveguide, coupled to the cavity through the 2 apertures, 2 slits, and the cavity resonates, right? The cavity resonates here, and some energy the cavity radiates through this partial reflecting surface. Partial reflecting means partially transmitting, right? So it radiates through the structure to free space, creating a beam in the both side direction upwards. So this is our paper we published in IEEE Transsections, Antennas and Propagation. Then some examples of 2D FSS type resonant cavity antennas. So in these antennas, the superstructure is printed circuit board type FSS. It can be either printed circuit board type or any other frequency selective surface FSS with printing on both sides or one side. In this case, the metal printed pattern is underneath on the bottom side. All you see in the top is just dielectric RT duroid. And the main advantage of this type of antennas is they are very, very short, because the height of the antenna is almost the height of the cavity, which could be lambda naught by 2, okay, half a wavelength, half a free space wavelength normally. But there are ways to reduce that if you want. There are papers published by Ferricides, etc., with resonant cavity antennas that are shorter than half a wavelength, like quarter wavelength. In those, you don't use a conducting ground plane. Instead, you use an engineered ground plane, like artificial magnetic conductor. The other difference here is the feed. In this design, the feed is not just one slot, it's a slot array. It's an array of slots feeding the resonant cavity, which is unusual. Normally, we use one element or few elements, not so many elements. Okay, this is another example of PCB type. I will come back to this one later, but just to give you an idea, I will come back to the design part of this later. So this is FSS printed on a substrate, dipoles, two dipole arrays, one above, one below. You don't see the dipole array in the bottom surface. And the resonant cavity is AR here. This is the ground plane, and this is the feed. So we got 13% half power directivity bandwidth, or 3 dB directivity bandwidth from this antenna with a gain of 16.7. That was kind of set record during that time in 2012. There are more resonant cavity antennas inspired by 1D periodic structures. You already seen this, right? This is a linearly polarized one. This is a smaller version of that, more sophisticated, with multiple dielectric layers. There's no metal here in the superstructure. It's total dielectric, all dielectric superstructure. This is the resonant cavity. This is the ground plane. So the difference in this antenna is it's a dual band linearly polarized antenna. It's a dual band antenna. So if you want to make a dual band antenna, you got to do two things. One is you have to design the superstructure dual band in such a way that the cavity resonates in both bands to make the cavity dual band. And then you feed it with the dual band patch or any other antenna, dual band. One example is a dual band microstrip patch antenna. That's what we did here. So I can explain how you design these things later. This is also dual band RCA, similar method, but this is a circular polarized dual band antenna. So you design the cavity to resonate in two bands, like before, and then you feed the cavity using two. In this case, we are using two different feed antennas, dual band circularly polarized. One CP antenna excites left-hand polarized waves in one band. Other one excites right-hand circular polarized waves in other band. So it's dual band. One band is left-hand circular polarized, other band is right-hand circular polarized. Which is not too difficult to do. These are standard corner truncated microstrip patch antennas. Not high gain, low gain, low directivity antennas, but when you use them in resonant cavity antenna, you can get high gain, high directivity. That's another linearly polarized dual band antenna. So in this one, again, we designed the cavity to resonate in 2 bands. This is opened up, like when you operate, we close it down. So design the resonant cavity to operate in 2 bands, and then we need dual band antenna to excite it. One way to do it is using stacked patch microstrip antenna. So that's a normal microstrip. This is the lower patch, and this is the upper patch. They have different dimensions, so they resonate at different frequencies. By tuning the patches, the dimensions, you can make this to operate in 2 distinct bands. It's very common way to make dual band antennas using the stack patch microstrip technology. And then we use the RCA to increase its gain and directivity. So a lot of those antennas are large, several wavelengths by wavelengths. This is a smaller one. Some of them are large. This is a smaller one. In the later part of our research, we were designing a lot of smaller resonant cavity antennas. Watch these dimensions. The area of the substrate is 2 lambda naught by 2 lambda naught in this one. It's 1.5 free space wavelength times 1.5 free space wavelength in this one. So they're very, very small. Our original antennas were like 5 lambda naught by 5 lambda naught or 6 lambda naught by 6 lambda naught, 36 lambda naught square area. But these have what, 4 lambda naught square area or even less. Now you may ask about the ground plane size. In this case, the ground plane is a little larger than the substrate area. But in some examples, as you may have seen, the ground plane has exactly the same area like the substrate. So you don't have to make the ground plane much larger. There's another paper in nitrophilic transactions on these antennas. Then we design this totally different class of resonant cavity antennas that has a significantly different dielectric profile. Now we change the dielectric constant in the transverse direction. Like this is the antenna, this is the axis of the antenna. You can see different colors. That means these are different dielectrics. So here we are changing the dielectric constant in the transverse direction on XY plane. So we call this RCAs with transverse permittivity gradient. This is our first transaction paper on this topic, if I remember correctly. You can find a lot of details. You can have a lot of different dielectric values or continuously changing dielectric, but you don't need that many. In practice, it turned out that you need only 3 or 4 dielectrics to make this. That is enough to get excellent performance. So otherwise, it's very similar resonant cavity waveguide and the feed, etc. So now we can compare the 2 types of small resonant cavity antennas with all dielectric superstrates. This is with different dielectric layers. Dielectric constant and thickness changes in the axial direction. That means we have axial permittivity variation. In this one, we have transverse permittivity variation. Both of them can be used in resonant cavity antennas. So you may ask which is better, right? And it turns out that this one is better than this. We figured this out later. We done a lot of research, lot of prototyping of this. But then I figured out if you try to do this, you might get better performance and in a shorter antenna. So I came with this idea, told Rahil and a few others. And Rahil was pretty good in this. So he came up with a lot of designs and some of them were published. So putting side by side, these are the ones with axial permitted variation, a circular version of that. This part is actually this whole part is the superstructure. This is the resonant cavity. It is not air in this case, it is foam that is to hold this, but foam is very much like air, low dielectric constant. So it's a foam filled resonant cavity, and then the ground plane is this. And you can see the diameter of the ground plane is exactly the same as the diameter of the resonant superstructure. So you don't need large ground planes. And the same in this TPG type antenna. This is our first TPG type superstructure. Looking from the top, only 3 different dielectrics. Looking from the side, that's the superstructure. And then the resonant cavity ground plane, same diameter as the superstructure. This is the feed slot and a waveguide. Right? Very simple configuration wise. Now I mentioned about high radiation efficiency. What if you have measured gain and directivity, you can very easily figure out the RF efficiency. The RF efficiency of the antenna is the difference between the measured gain and measured directivity. So you can see this blue curve is the measured directivity, green curve is measured gain. It's almost identical, very small difference between the two. So this antenna has very high efficiency and very low loss. And it has good gain and bandwidth over a range of frequencies. But this is not our best. Now about the size. Why did we make them smaller? Right? I said the old ones were very large. Newer ones were smaller. But smaller is better in several ways. Smaller is better in several ways. You can install it in a space in systems that has space constraint, limited area, right? In communication systems, so whatever application you're looking at, if you have a space issue, usually these days everyone wants to make everything compact. So you have a problem with space, so the smaller the better. And because it's smaller, the manufacturing cost is less, especially the consumable cost like dielectric. So those are the secondary issues, but the reason we made them small is not any of those. It is something quite unusual in antennas. See what happens when you make this antenna. This is a particular type. When we make the superstructure area smaller, starting from very large, like 36 lambda naught square, we are making it smaller and smaller. Okay, and we look at the peak directivity. We get pretty good directivity from antennas of this size. There's no need to make them larger to get higher directivity, and in fact, directivity can drop due to various issues when it is too large. If you make it very, very small, then directivity will probably drop. So this is a good range to get very good directivity from a small antenna with an area of the order of 5 lambda naught squared to maybe 10 or 15 lambda naught squared. But there's another even more convincing reason. Look at the bandwidth. This is the bandwidth scale. Bandwidth graph is the green curve. See what happens when you make it smaller. The bandwidth increases. Right? The bandwidth increases. So here you have a small resonant cavity antenna with the same directivity as bigger ones, but more bandwidth. That is fantastic, isn't it? But there's one issue. If you try to make it very, very small, like here, although bandwidth is large, the side lobes may be too strong. So depending on your side lobe requirements, there's an optimal size somewhere here. You get good directivity, good gain, very good bandwidth, and low enough side lobes. That's how you would pick the size of these antennas or optimize the size to get the best performance. And that is true for both APV type, TPG type. These are quite small. You can see the area is 1.62 lambda naught squared. Bandwidth is still better than 50%. Percentage bandwidth, directivity 18 dBi. But this is the old type. Now go to the new type with transverse permittivity gradient. We analyze antennas with several steps. One thing common in all of them is the center dielectric has the highest dielectric constant, and they monotonically decrease. Monotonically decrease from center to the edge. Epsilon 1 is the largest, epsilon 5 is the smallest. And we look at the variation of bandwidth and gain or directivity by changing the thickness of the superstructure. Simple T here is the thickness of the slab. Very hard to see, that's the thickness of the slab. All dielectrics same height. So what we're doing here is we're changing T and plotting directivity versus frequency for different values of T, increase in T. The thickest thickness is not a lot, it's between 4 millimeter and 5 millimeter, right? The thickest one, the thinnest one, 4 millimeter, got the bandwidth of 49% and a peak directivity of 17 dBi. At the other end, the thickest one, 5 millimeter one, got about 39% bandwidth and 18 dBi peak directivity. So there's some compromise you can make. You can get more bandwidth by compromising the directivity and gain a little bit by changing the thickness of the superstrate. So you've already seen this antenna, but this is its measured gain and directivity, how it varies with frequency. Variation is less than 3 dB, peak directivity 16.4 dBi, cross-polar levels, and the gain bandwidth, 3 dB gain bandwidth is 54%. 54%. Or we have gain better than 15 dBi over a 54% bandwidth. No, that is wrong. We have 3 dB gain bandwidth of 54%. The peak gain is greater than 15 dBi. Actually, accurate is 16.4 dBi. That is somewhere here. Okay. So that is a good selection of antennas. But if you are an antenna engineer, you probably want to know how you design these, right? This is like a catalog and their characteristics. If you want to pick an antenna for your application, that will help. If you want to design an antenna for a particular application, that part of the lecture will guide you to select what to select, what type of antenna, considering the space you have and the other constraints, the cost, performance, etc. But now I'm going to, when we come back after the break, we will look into design methods for resonant cavity antennas. Little bit theory in some of those. I will not go into a lot of equations, maybe in one or two. Few slides you have equations, but more focus in design. So are there any questions? We still got like 2 minutes before the break, I guess. Any questions before we break out? Yes, go ahead, Kumari.
Am I audible? Am I audible?
Yes, yes.
Okay, so good evening, sir. First of all, thank you for such an insightful lecture. My question is regarding the tunability of TPG and APG in resonant cavity antennas. Like, have there been any studies or practical implementation where there is like the structures can be
Sorry, your voice is very faint. Can you speak a little bit slowly and loudly closer to the microphone?
Okay, okay.
Little bit louder.
Is my voice clear right now?
Yeah, that is good. That is better. Yeah.
First of all, good evening, and thank you for such an insightful lecture. So my question is regarding the tunability of TPG and APG in resonant cavity antennas. Like, have there any studies or practical implementation where the structures are dynamically tunable to adapt varying frequency? Like, could be integrated with some materials like graphene, as we know that they can be tunable, their conductivity is tunable, so that they can be implemented in applications. So this is my question.
There are a lot of papers that cited our original paper. So I can't say for sure exactly what has been done and what hasn't been done. But there's a lot of scope to try different material, including 3D printing and other manufacturing methods. Because with those methods, you can basically, you want to have a dielectric, effective dielectric constant changing with radius, right? With R.
Okay.
That's all. So there may be some studies, but I'm not sure about graphene, etc. Because I'm not top of every paper that happened after this. But I think there's a lot of scope.
Okay. Thank you, sir.
Thank you. So we will return in 15 minutes, right? at sorry, no, actually, so it's at 1 hour. I forget the schedule. So let me check. Yeah, in 45 minutes, right?
Yes, sir. Yes.
We come back in 45 minutes. That's 2 p.m. your time.
Yes. Yes.
Okay, then. See you then. Bye.
Okay, sir. Thank you.